So in this final lecture we will prove the Urysohn's metrization theorem. So let's begin. Right. So let X be a regular and second countable topological space. Right. So recall that regular meant that we can separate points and closed subsets by disjoint open sets, and second countable meant that X has a basis whose cardinality is countable. And in one of the previous lectures we had proved that these two assumptions imply that X is normal, right? So then X is metrizable. Right? In other words, we can put a metric on X such that the topology induced by the metric, So in other words, this means that we can put a metric on X such that the topology generated by the metric is the same as the topology on X that we started with. So let's see how to prove this. So the idea is to use what we proved in the previous lecture, that Rn, the countable product of R, is metrizable, right? As Rn is metrizable, it suffices to produce a continuous map f from X to Rn such that 1, f is an inclusion, and 2, when we look at f from X to f of X, so this f is an inclusion, so this is going to be a bijection, right? So this is an open map. So this is a bijective continuous map and f is also open, right? So that will mean that there is a homeomorphism, right? So here f of X has the subspace topology from Rn. Right. So the subspace topology from Rn is induced by the metric, because the product topology on Rn is induced by the metric, as we saw, and this will imply that the topology on f of X is given by a metric, but f from X to f of X is a homeomorphism. That will mean that the topology on X is also coming from a metric. Right? Okay. So or equivalently, we have embedded this f is going to give an embedding of X into Rn, and okay, so let B be a countable basis for the topology on X. This is because X is assumed to be second countable, right? So consider pairs V comma U such that V comma U are both basic open sets and V closure is contained in U, right? So by Urysohn's lemma, there is a continuous function f sub V comma U from X to 0, 1 such that f sub v comma u of v closure is equal to 1 and on x minus u this is equal to 0. Okay. So we have so the collection of such pairs where v closure is contained inside u, that's a, so first of all we have many such pairs, right, because given any point x we can first take a basic open set u inside that, then as x is normal, well x is regular and second countable and we have proved that it means x is normal, we can find first one open subset v inside x such that v closure is contained inside u, and inside this v we can take a basic open set w which contains x. So then w closure is also going to be contained inside u, right. So there are many such open sets, there are many such pairs, right, but at most they are going to be countable because v is in a countable set and u is in a countable set and a product of countable sets is countable. So we have a countable collection of continuous maps from x to r. Yeah, so we put these together to get a continuous map. Right. So using the property of giving a map to the product, so we get this map f from x to product over all these pairs u comma v r, right. There is a count. So v comma u such that v closure is contained in u, right. And what is this map? Given a x, it goes to this f v comma u. Okay, so there is a countable product. Right, and there is a countable product, so therefore this is, I mean, we can enumerate such pairs and then this is going to be equal to r n, right, and therefore this, the product topology over here is coming from a metric because of our previous theorem. Okay, so clearly, okay, this map is continuous, we have already observed that, right. So let us prove that this is an inclusion. Right. So if x is not equal to y and both these are points in x, right, so then there exists basic open sets v comma u such that x is in v, is contained in v closure, is contained in u, and y is not in u. Right. So we can just take this x and this y. We can first start with u over here and then we can find v. Okay. So then f v comma u of x is equal to 1 and f v comma u of y is equal to 0. Okay. So thus these 2 points f of x and f of y differ in the v uth coordinate. Right, which implies that f of x is not equal to f of y. Okay, this shows that this map is an inclusion, right? So this implies f is an inclusion. Right, and next we need to show that x to f of x, we have this f, and this is an open map. Right. So what do we have to show? So that is, given u in x, which is open, we need to show that f of u is open in f of x. Yeah, f of x has a subspace topology, right? Where f of x has the subspace topology. So to do this, it suffices to show that if x is a point in U, then there is an open set Y contained in this product such that f of x belongs to Y intersected f of x. This is contained in f of u. Right. So our aim is to show that f of u is open. So let's say this is our f of u. So given any point in f of x, right, we are going to show that there is this open subset in, so Y intersection f of x, that's open in the subspace topology, which is completely contained inside this f of u. So that is what we have to show. Right. Okay. So for this, find basic open sets W and W prime such that x belongs to W, is contained in W closure, is contained in W prime, is contained in U. Right? And consider the projection by W comma W prime. So from this product, U V comma U's to the W W prime's coordinate, right? Yeah. So W W prime also occurs, the pair W W prime also occurs in this collection of pairs because W closure is contained in W prime, and these are basic open sets, right? So therefore, so this map is okay. So we have, this is the projection map, and let Y be equal to pi W comma W prime inverse of 0 infinity. So then Y is open in this product. Okay. So by definition of f, when we look at the composite x to f, and we project to W W prime, this composite is exactly f W W prime, right? And as x belongs to W closure, this implies f W W prime of x is equal to 1, which is in 0 infinity, right? But this f is equal to pi W W prime of f of x, right? And this is in 0 infinity. This implies f of x belongs to pi w prime inverse of 0 infinity, this is equal to y, right. So this implies that f of x is in y intersected f of x, right. So that proves this this part. So now let's prove this inclusion, right. So suppose f of a is in y intersected with f of x, right. So this implies that f of a is in pi w prime inverse of 0 infinity, which implies that pi w prime compose f of a belongs to 0 infinity, right, which is same as saying that f of w prime of a is in 0. So now note that f w prime of w closure is equal to 1 and f w prime on x minus w prime is equal to 0, right. So therefore, since f w prime of a is in 0 infinity, so this implies that a has to be in w prime and w prime is contained in u, right. So as a belongs to u, this implies that f of a belongs to f of u, right. So thus we have proved that y intersection f of x is contained in f of u, right. So this proves that f of u is open. So this completes the proof of this theorem. So we will end this lecture here, and this also brings our course to an end. Thank you very much.